In the microscopic world, countless microorganisms, invisible to the naked eye, are living and shaping different types of soils and environments. These microorganisms affect land use patterns, soil health, carbon stock, and therefore climate. However, they tend to be overlooked aspects when policies are developed. Planetary health and the fight against climate change are prominent issues in the current environmental scenario. However, they have been faced with sets of policies and strategies acting on various scales and shaping different landscapes around the globe, disregarding the microscopic dimension that should be central to the policy development. Chief of these policies are ones related to mass afforestation, leading to an increase in forest cover. These policies, issued by global organizations dominant in the global north, are implemented mainly in the global south, shaping the visible and invisible landscapes. Under the net zero policy, big countries and companies tend to offset their emissions through a carbon crediting system. They have catered for greenwashing, displacement of small landowners, and created major land use conflicts. Therefore, we start questioning, is the right tree in the right place? And is the intersection of forests with other land uses still valid to achieve net zero? To map out the land use conflict, we have focused on the woodlands and peatlands as the major terrestrial carbon sinks of the globe. Due to their coexistence, they have lost their ability to sequester carbon and have become carbon emitters. This conflict can be clearly monitored in the UK since 12% of its land is classified as peatlands. At the UK scale, the distribution of peatland, woodland, and their intersection areas is mapped. It is clearly noticed that the intersection areas are dominant, emphasizing on the land use conflict mentioned. Do we need a net zero or shall we aim for a real zero? Are these policies and strategies adapted to actual site conditions? How can soil and its microorganisms shape and be shaped by policies? The objective of the project is to look at how both land uses are managed and exploited to design policies and land assessment tools that can address the conflict between the two entities at macro and micro scales. The structure is based on the analysis of peatlands and woodlands in the UK. First through a timeline, a temporal analysis of their existence and coexistence, then through a spatial analysis of each land use independently. In the 1920s, peatlands became part of the reforestation projects as lands of low value, or wastelands in the UK. It lasted up until peat action plans have been issued and then peatland strategies to conserve and restore peat. Peat accumulates by 1 millimeter of organic matter per year. Therefore, it takes around 3,000 years for a 3-meter average depth peat to form. Peatlands are diverse and complex ecosystems. They are home to several animal and plant species, especially sphagnum moss. They sequester more carbon than any other type of terrestrial ecosystem, exceeding the global above-ground carbon stock of forest ecosystems. Water table in healthy peat is usually very high, where water can be easily recognized on the surface of the land. However, the state of natural peat is rare in the UK, where almost 80% of peatlands are in damaged states due to human intervention. They turned from being carbon sink to carbon sources. The map shows the distribution of peatland types, green highlighting blanket bog, the yellow is fen, and orange is raised bog. As for peat production, it is based on extraction and drainage. Extraction has been categorized into domestic and industrial ones, serving different productions. Due to forest management policies and the aim to increase forest cover by set deadlines, the forest cover in the UK has increased over the past century and is most notable in Scotland. Woodland species in the UK are divided into native and non-native ones. Native species are classified into semi-natural woodlands and ancient semi-natural ones, mostly dominant in Scotland and southern England. 2/3 of them are privately owned by individuals and groups, and only 1/3 is publicly owned. Due to the lack of native species in the UK, non-native ones were introduced to support reforestation attempts. Sitka spruce dominating in Scotland and Wales, and the same applies to lodgepole pine. Most of the non-native species plantations lie within the commercial forestry category. They supply the timber production industry. By addressing the management and exploitation of both land uses at a national scale, we aim at expanding a policy and designing a land assessment tool that will address the conflict of coexistence between woodlands and peatlands and tackle peat restoration in Scotland. Making use of existing initiatives, expanding on existing land assessment tools, and looking into mapping techniques to understand the geomorphology of the peatland areas. We tackled existing community-driven initiatives in Scotland. Sites were selected based on areas of conflict, land ownership, carbon crediting systems, and peat action plans. One of the sites is owned by John Mayer Trust. This complex site is based on the intersection of peatland and woodland, with complete and ongoing restoration projects of peat. Through time, the site has been subject to various policies and strategies that shape the land. Our aim is to gather the knowledge into assessment and restoration manuals, where we come back with policies that are not only related to the technicalities, but expand to tackle the way communities manage the land. With respect to the policy part, the carbon emission land tax is a proposal that has been suggested by John Mayer Trust as a contribution to maximize the carbon sequestration storage potential of land in Scotland. We have developed this policy further, in addition to a land assessment and management tool. These can be accessible through a platform that will allow landowners and users to assess and manage their lands with the help of experts, NGOs, community trusts, and the community members. Our structure is highly influenced by our meetings and discussions with policy directors of various community trusts and organizations. We have had a thorough discussion with Mike Daniels, John Mayer Trust's policy director, and the Trust's land managers, in addition to attending a conference in Scotland where we had the chance to discuss with various stakeholders. This proposal has been developed by John Mayer Trust as an expansion to the policies and strategies developed to tackle climate change. The aim is to maximize the carbon sequestration potential of land in Scotland. They proposed a carbon emission land tax for large-scale landowners with properties above 1,000 hectares. Based on hectareage, every landowner would be assessed for actual and potential carbon emissions and sequestration by relevant public agencies, local authorities, and expert consultants. Landowners would then be placed in a graduated banding scheme controlled by local authorities. Those landowners eligible for the tax could move to lower tax bands by changing land use to maximize carbon sequestration. One of the main goals of this taxation is to drive positive behavioral change. We have built up on this tax proposal, first by modifying its criteria. Lands included will be classified into over 500 and under 500 hectares, creating carbon equations that would calculate actual and potential carbon emissions, in addition to expanding the proposal to include a funding scheme that would support the small landowners and the fragile community included in the new management plan. Second, the revenue will not only be used to further restoration and expansion projects, but will also be used to support the community, especially in owning land. Third, by elaborating on the suggested tools. Our strategy is based on a land assessment tool that includes a soil, water, and timber assessment mechanism, carbon tax calculation, land management proposal, and a land management implementation or final design. The following explains how the tax works. For lands above 500 hectares, an initial carbon tax is issued based on the actual carbon emissions. If the landowner decides to change land use and abide by the proposed land management scheme, a new carbon tax will be calculated. This tax is lower than the initial one. However, the tax would increase in case no change is implemented. In addition to the increased tax, a fragment of the land will be placed under the management and in some cases ownership of the community. It will fall under the community's right to buy abandoned, neglected, or detrimental land created by Part 3A of the Land Reform Act. It gives community bodies a right to purchase land which is wholly or mainly abandoned or neglected, or the use or management of the land is causing harm to the environmental well-being of the community. As for lands below 500 hectares, no tax is applied. Instead, they can apply for funding in order to enhance their land conditions. This funding is part of the revenue collected from the carbon emission land tax and large landowners, in addition to existing funding schemes such as the Peatland Action Fund by Nature Scot and the Scottish Government. The development and design of the assessment manuals was based on our personal experience in the field trip. The following will show a segment of our site visit to better explain the process. Our field trip was based on community-owned and managed lands. However, we expanded our scope of work and research into some private lands to create a comparison between land conditions based on various land ownership. We visited Loch Rannoch-Schiehallion area in Scotland, followed by Glenridding in Lake District, Northern England. In the area of East Schiehallion, we have visited 4 sites, 2 of which were thoroughly assessed. Based on GIS data and the suggestions from John Mayer Trust, one of the sites we visited is an intersection of peatland and woodland in Brace of Foss. Trees were planted on peatland. We recognized a lot of cut down and falling trunks with roots and soil completely exposed. We tested the moisture and pH values of different layers of soil. From the section we dug, you can see the difference between shallow soil and deep soil, followed by the aggregation test and infiltration test. In addition to the soil samples collected from different layers, we also used a transparent tube to collect a soil section for comparing it with soil conditions from other sites. Moving to the second site, Pitlochry. This site is a good condition peatland at the border of the site East Schiehallion, owned and managed by John Mayer Trust. We recognized it from the special vegetation layer, soggy ground, and puddles. On GIS maps, it showed a shallow peat adjacent to the woodland that is being cut down, except for the native tree species. Then we started to test the soil attribute. It was easy to insert the monitor into the soil. The site recorded a pH of 6 to 7 and the value of moisture is very wet. Next, we used the soil sampler to see and collect soil samples from different layers. The soil between 5 to 10 centimeters were quite black and dark, and the color of deeper soil was a bit gray. We used samples from different depths of the soil to test the aggregation. Soils were sticky and stable. In terms of water infiltration test, due to the high water table on site and it appearing on the ground level, there was a slow water infiltration. Finally, we used a transparent tube to collect the soil section and well documented our test. The following is the assessment manual that developed based on our field trip experience for the landowners to recognize and identify peatland and woodland conditions from soil and vegetation. The manual is divided into 4 parts: soil sampling guide and tool preparation, peatland condition and vegetation identification, woodland health and species identification, and the last part is the microscopy of soil. In the first chapter, soil sampling tools are listed and the different processes from using the map to locate testing sites to collecting samples are explained. In the next chapter, it shows how to recognize peat soil, the identification of peatland condition, and most importantly, the vegetation of peatland, various sphagnum moss species. In Chapter 3, the ways to inspect the health of trees are provided, in addition to suggestions for removing and planting non-native and native tree species are listed with their specific features and needs. In the last chapter, the knowledge of microscale of soil under the microscope helps people further identify the characteristics and health of soil from different types of bacteria, protozoa, fungi, and algae.
In order to provide access to the suggested tools, we have developed a platform where the users will have the ability to reduce their lands, undertake the assessment, and be provided with the right management scheme. This platform will also allow the users to engage with experts and community trust. The platform structure is divided into steps: inputting land data, land assessment, carbon tax, and design menu. Each of these have subcategories. This platform will also be shown in coordination with our land assessment and management tool structure shown through the structure below. The platform starts with an overview page where the user can browse through different map scales and get the chance to look and engage with different complete and ongoing projects. Projects such as the ones in the Highland area. The user would enter the land number and the property information would show up, and the user would specify the ownership. The platform also provides property information of neighboring sites, such as the following example. Hypothetically speaking, we will assume that Drummond Trust has acquired neighboring land. The user can check the site morphology too. This will provide a detailed and deep analysis of the site conditions and layers. Next, land use data is required. The user will enter the current land use. Simultaneously, computer-generated areas of different land use is shown. One can select a specific land use to get more detailed information. By moving to the next step, the user would need to specify the status of the land assessment. They could press yes if they have previous land assessments done. In this case, they will be required to enter the assessment date, upload reports and necessary assessment maps. If they have no previous assessments, they can book an appointment with experts, download the report, and apply for a toolkit. When downloaded, the report will allow the users to understand the site condition by highlighting the color, specifying moss species and tree species. They can also take samples back for microscope analysis. After using the manual, the user will input the results on the platform page, and results will be computer-generated with the supervision of experts. The following shows how the results will be displayed for the users. Set images will be used as a background to help the users identify the area. At first, the location of the sample will show, followed by the highlighting of the water feature, followed by a soil section of the site, showing the different layers. From the samples collected, different peat soils will be identified, such as peat and clay. This is accompanied by a pH analysis of the site. A microscope dimension will also be added to further explain the results. It shows in the case that the site had previously a high water table. Then a description of the different tree species on site is shown. First specifies the non-native layer than the native one. This is also done for more species, where using the vegetation sample for the site can help identify the species that make up the ground cover. Finally, a conclusion is provided summarizing the condition of the site and percentage potential of the restoration. Based on the land assessment results, an initial carbon tax is calculated. It is assumed of the actual carbon emissions from the various intersection and pillar areas. These areas are identified and each one has a detailed analysis of the carbon emitted. On the left side of the platform, a carbon scale will show the total carbon emissions alongside a taxing bandbar to show how much tax will be paid per hectare per year. As the user gets an idea of the initial tax, a set of strategies will be provided at this scale. This is followed by an option where the user will need to specify the area in which the strategies will be implemented. In this case, Area 3. It's the site we have visited and analysis in Scotland. By moving to the next step, the platform generates a three-dimensional view of the area with the relevant site strategies. Before the final decision, a discussion forum allows the user to get the community's feedback through voting, asking experts, and chatting with community members. The user will be able to navigate through the different strategies and check their implementation on site, such as cutting down the trees, wood for timber production, or filling the wells, raising the water table, introducing more species, and refilling the peat banks. In the case of cutting down non-native trees, in the short term by cutting them down, less carbon will be absorbed. However, our aim is to enhance land conditions for long-term carbon sequestration. It is followed by an option where the user can navigate through time to understand the change on site, existing and future schemes. Upon agreeing, a second tax is calculated which is lower than the initial one since Area 3 is considered a carbon sink and it has a negative potential carbon emission value. The user would pay the tax, which is collected by the government and will be monitored to check the implementation of the management scheme on site. One last step is the land assessment scenario, where an existing and future scenario of the site are shown. The existing showing the site conditions and the strategies applied. On the other hand, a 2045 scenario is provided to show the positive consequence. We want to utilize our tools to enhance the transparency of land ownership in Scotland, create a transformation in how lands are used and managed in order to transition to a real zero. Our next step is to share our policy development, tools and platform with the community and its organization, especially John Muir Trust and Community Land Scotland, and receiving feedback to follow ground our proposal. Upon developing the project, we have come across many areas of interest and conflict. How can we integrate the carbon credit scheme to become community-oriented ones? How far can the policy strategies and tools developed increase the environmental awareness and drive a positive behavioral change among landowners?